Hey guys, so today I'm presenting on my paper which is based on an architecture for control and communication in distributed artificial intelligence systems, or DIA system for short. So what does a distributed artificial intelligence or DIA system means? Well, it consists of multiple physically separated processing nodes with each of them having at least one expert system. It is characterized by the information of the knowledge source of its system and the information of input data at each node. That is, the main characteristics of the DIA system is the completeness and exactness of knowledge system in expert system. As I said before, each node will be having an expert system, and the characteristics is that the node will depend upon the expert system to know what information the node will be holding or what information it has to process. The use of DIA should reduce the communication bandwidth needed in a distributed processing system as the communication will be happening on a higher level. This paper will also address these issues through the architectural design of a DIA system focused on control and communication aspects. The system will be dynamically self-organized and can improve its performance during operation. Now, why do we need a DIA system? Certain problems are too large for a single processing node to handle. That is, in a distributed sensor, let's say in a distributed sensor network, where each node has only partial information about the environment, it won't be able to process all the details. And another example would be an air traffic control system, which requires managing vast amounts of dynamic data across different regions, or an engineering design system, which requires knowledge distribution across multiple hierarchical levels. Now let's take a centralized system. It also struggles with different issues like scalability, reliability, and resource overload. Scalability in the sense like they become bottlenecks as the problem size increases. Reliability in the sense like a single point of failure can compromise the entire system. And resource overload, which means a single node cannot efficiently process large distributed data sets. Another issue is the partial and incomplete knowledge. Now, what does it mean? Well, in a real world problems, as I mentioned before, individual nodes or systems often have a partial view. That is, it can access only a subset of the environment data. Like, let's say, for example, in an air traffic control, each node handles only flights in its region. Incomplete knowledge means the node may lack the information to solve the problem entirely. Hence, the need for a DI system. Now, what is the goal of the proposed architecture? First one is iterative refinement solutions. That is, the problem solving approach is by breaking the main problem into sub-problems. And these sub-problems or kernel level problems are synthesized by the kernel level problems are first solved and then synthesize the results dynamically. Now, if the problem is not solved, then it just continues refining until the problem is solved, or it results in a situation where the problem is not solvable at all. In which case, it will move the process to another node. It also improves the performance dynamically, meaning the system will use learning mechanics to adjust itself based on the knowledge it accumulated from the node or based on the information from other nodes, meaning it will be improving dynamically. It reduces the communication bottleneck. And it does it by minimizing the unnecessary messages by using methods like directed transmission when possible, thereby reducing the overhead and bandwidth usage. It also incorporates dynamic planning and focus control. The system dynamically plans and controls its problem-solving efforts, focusing on the most promising solution paths to reduce the size of the explored solution space and errors during computation. Now, to the system architecture overview. In this architecture, all the processing nodes have identical organization. Okay, so each node will be consisting of a front-end processor or a front-end receiver, planner, scheduler, solver, blackboard, meta-level knowledge, and knowledge sources, as you can see from the figure. Now, what does the front-end receiver or processor do? It manages the communication with other nodes, including sending and receiving tasks and results. The planner, on the other hand, develops problem-solving plans by using meta-knowledge to decompose the problem and choose a solution strategy. The scheduler then assigns priorities to tasks based on factors like importance, difficulty, and resource availability. The solver executes a problem-solving plan by invoking knowledge sources and ensuring quality through iterative refinement, which means like it will continue till the problem is solved. If not, it will use the communication mode to send it to another node so that it can be solved there. Now, what is a blackboard? It is a shared data structure that stores tasks, plans, and results to enable collaboration between processes within and across nodes. The Blackboard is also organized according to task orientation and timeframe structure. Then we have meta-knowledge database, which stores knowledge about the capabilities of the node itself and other nodes to guide the problem solving and communication. In this case, the system can learn both kinds of knowledge and information is exchanged during problem solving. Now, the knowledge source. It encapsulates the domain-specific expertise for solving the task. The Blackboard, I'll explain it a bit more in the sense it basically stores data. The data that it stores are like related, it's mostly data structure information which is related to the task, plans, and also the final results so that it can send it back so that it can be used again for the planner and the scheduler. Now let's move on to the problem solving workflow as to how when a task raised the process, how it works. So when a problem or a task is like introduced into the system to one of the nodes, the front-end processor accepts the incoming task or message, verifies whether the task is relative to the node using the meta-knowledge, then generates a task frame on the blackboard to store details like task identifier, data plane expected, results, quality, etc. If the task is outside the node's capability, then it will be transferred to other node which will probably be able to solve the process. The planner will then break the problem into more sub-problems and will create a problem-solving plan and adds the plan to the blackboard for further processing. The focus control mechanism selects the most prominent subtasks based on their cost, the resource requirements, and other factors. It helps restrict the solution space by narrowing down which tasks should be explored next. The focus control mechanism influences which tasks are selected for execution by the solver. The subtasks along the selected solution path are marked as ready for execution. If the systems detect any errors or inefficiencies in the current plan, the focus control mechanisms helps refine the solution path by dynamically adjusting the subtask to be executed. The solver. It initiates the execution of the subtask based on the current solution plan. It involves the knowledge source to the solved. So as you can see from the figure itself, the front task receives the front end receives a task that needs to be planned. So what it does, it checks with the meta level knowledge to see if it's possible to process it or not. If it's not able to process it, then it will send to another node which will be able to process it, and then it's sent, and the planner will then take the task and then break it down into smaller tasks, and it will store the meta information on the blackboard, and then it will move to the focus planning. And the focus planning mechanism is mainly used along with the scheduler to restrict the solution page so that all the information, so that all the tasks won't be sent to the solver at once. Instead, it will be sent, like the important messages will be only sent to the solver. That's the main purpose of using a focus control mechanism. The solver will then initiate the execution of the subtask based on the current solution plan. And it invokes knowledge source to solve the subtask. That is the subtask which the scheduler will send to the solver. The solver will try to solve it using the knowledge source that it has. And the result, which is like the will be combined, and the completed subtask will be into a partial or a final solution. The synthesized result will then be stored in the black box. Now, if the subtask will fail or like it produces a suboptimal result, the planner dynamically will adjust the problem solving plan, and the focus control mechanism rewrites the solution path and then selects like an alternative subtask. This iterative process continues until all tasks are successfully resolved or deemed unsolvable. The meta level knowledge will then be updated based on the nodes. That is, the nodes adjust their estimation of taskers, execution time, and capabilities based on the problem solving experience, right? So the knowledge is then refined and improved for like future performance. Once all subtasks are resolved and results are synthesized, the complete solution is provided to the requesting entity, which is like another node. Now, let's talk about the key features. The key features of this system is that the system process the scalable problem solving. That is, the system process complete complex tasks across like multiple nodes with distributed expertise, enabling the system to scale efficiently as the problem size increases, since it is using like multiple nodes. Efficient task execution, right? So we use focus control mechanism which will dynamically prioritize and select the most promising subtask. It's not going to send all the tasks, like there won't be any unwanted messages. Only the most promising subtasks will be sent to the solver, so that it will reduce the any unnecessary computation, uh, and also minimizes the task execution time. It also optimizes the communication by using directed communication, which like significantly reduces the message traffic after nodes accumulate like experience, and which leads to like longer communication overhead. Initial broadcast communication ensures the node gain enough knowledge to make the direct transmission. And this is the performance metrics. The task reduction, the number of subtasks executed for like a 2-bit adder decreased from 22 to 16 after incorporating the learning process. The communication directed transmission reduced the number of messages by up to 87%, which is pretty huge. And it also increased the scalability by dynamically adapting to new problem solving scenarios, maintaining efficiency. Now, some of the things that I would say can be done better would be some tasks will get delayed due to the dependencies on like other tasks, especially when the subtasks are being solved by distant nodes, right? And a solution that I think might be like using task scheduling algorithms that will like prioritize the task based on urgency and dependencies. Also implementing like a synchronous execution so that the independent tasks will progress without waiting for others. The system will take time to accumulate useful meta knowledge. So another way to solve that would be to introduce like pre-trained models, which can actually make it a lot faster. Now, these are some of the real world implementations that it had. Since this paper is like a 10-year-old, so I was supposed to find some more information about this. And some of them that I found were like it is being used in like autonomous vehicles, for example, like Teslas and stuff, where the cars drive by themselves. So they require like a DAI system, um, a distributed artificial intelligence system, so that it is able to perform by itself, so that it can improve its state by itself by learning about the task. And it is also used in Amazon warehouse, like use of fleece robots to move inventory around the warehouse. These robots also use like DA to coordinate their movements and avoid collision. Even in IoT systems, like that is like in smart homes, for example, they use it. For example, let's say a thermometer, where it analyzes the temperature by itself and then adjusts the value, right, so that it can maintain like the most optimal temperature, which is also another implementation of DAI. So, in conclusion, I would say like the paper has designed a control and communication in distributed system which is scalable, flexible, and also demonstrate a significant improvement in efficiency and reliability and performance. It also extends to different domains requiring distributed decision making, like let's say robotics and a real-time monitoring. And that concludes my presentation. And these are the questions that I have, like what are the key components of the proposed DAI system? architecture and how do they contribute to task execution and communication, which is there in the paper, in the presentation. Also, how does the proposed DAI system dynamically improve its performance during operating system while reducing, which is by using a focus control system that I have mentioned before. With that, my presentation concludes, and I hope you have a wonderful day. Thank you.